In this video, we would like study from the theory of computation and answer a specific long-rooted question. Can all the problems be solved in polynomial time? I would like you answer this question in the end of this video. The title of this video is Tractability P, NP complete. We'll talk about different classes of problems. Some problems are actually undecidable or untractable, no matter you believe or not. Now let's take a look at some example. Suppose we are working on lab for a programming class, have written our program and start to run it. After 5 minutes, it's still going. Then people ask, your code include infinity loop? Or what's going on? It's too slow? It would be convenient, right? It would be convenient if we have a compiler which can tell us that our program has an infinity loop. Did you find any compiler who can perform this task? The answer is no. No any compiler can do that. And this is an undecidable problem. There is no program that will always correctly detect infinity loops. Just take a look at these small loops. This we have several inner loops. Take a look at this last loop. And when we take a look, it looks like everything is fine. And you have exit. And when this expression evaluated to be true, definitely it will exit, right? So from the syntax, when reading this code, from the syntax, it's no problem at all. And here, this is some students say this loop. No, we have exit here. And in each loop here, everything seems make sense. And also pay attention to here. This is the one statement. This is a for loop for this statement. This is a for loop for this statement. This is a for loop statement. Right? And then this is together. So after you have this total, this for last loop, then you change the x, right? Everything looks fine. But when we put in the flowchart, it's the same as this statement. When we try to analyze to see what is the results, and we found out this is an infinity loop. Let's take a look at another example, which is a Turing hunting problem. Give a program and input where the program will eventually hunt when run with that input or will run forever. So you may say, what is this problem, right? This is corresponding to the long-rooted question, can all the computer problems be solved by a computer? There are computational problems that cannot be solved by algorithm even with unlimited time. The Turing hunting problem is Alan Turing proved that the general algorithm to solve the hunting problem for all the possible program input pairs cannot exist. A key part of the proof is Turing machine was used as mathematical definition of a computer and a program. And take a look at this one. Give a program an input where the program will eventually hunt when run with that input or will run forever. this question very similar to what we said question before, which is infinity loop. Can we detect infinity loop or not? But it's changed a little bit. Alan Turing, when he was in your age, maybe a little bit older than your age, and he proved that. And his proof, it is in this very small C++ code, and give a computer program and some input to that program, where the program go into infinity loop when feed that input. So take a look at this one. They have several, three methods. The boost yet uncle method, and stops on self method, with the stop method, and stop on method. This on self method will invoke this one, and this bobs will invoke this one, right? Let's take a look at this method. And in this method, we say if it stops on the program itself, then it will return false. And actually here, it will have a loop forever. So it means if this program claim it can stop on itself, but actually it will never stop. It's something is ridiculous. So take a look at this code one more time. Either it runs forever or it stops and return true, right? It is or it stops, return true, or it runs forever, depending on whether the call to stop on self returns true or false. What happens when I try Bob's ear ankle on itself? If this gives the input, it is this code itself. This method goes into an infinity loop. It is because stop on itself returns true, which means that it would be stop return true, but this means that Bob ear ankle, this method would stop when feed itself as input. This contradicts the assumption that it goes into infinity loop. If this method, Bob's ear ankle, would run forever when feed itself as input, this contradicts the assumption that it determines. We have therefore led ourselves to a contradiction. This method stops only if it runs forever. Since this is impossible, one of our assumptions must be invalid. By tracing our reasoning backwards, we find that it's therefore impossible to have written would it stop in the first place. In other words, the hunting problem is undecidable. So this is the unknown's proof. This okay, let's assume the code could be given the program, and program tell this code can stop, but and when we add a little bit small code there, then actually in a way it cannot be proved. It cannot stop. So this is an undecidable question. And also here, if you're interested, you can take a look this video. If you're interested, you can take a look at this video, and this video is in our canvas. So for me, I just want to move forward. Some problems are intractable. As they grow large, we are unable to solve them in reasonable time. But how can we define what does mean the reasonable time, which is standard working definition, polynomial time? On an input of size n, the worst case running time is O n to the power of k for some constant k. And reasonable time also corresponding to O n square, O n cube, O1 constant, or O n log n, O to the power of n. And we see here, this is reasonable time or not reasonable time. When n increases to infinity, this is horrible. So this is a polynomial time. This is not polynomial time. Are some problems solvable in polynomial time? Of course. Many algorithms we've studied provide polynomial time solution to some problems. For example, maximal subarray, sum problem, Ballet heap, the Young-Tabner problem. Are all the problems solvable in polynomial time? No. Turing's hunting problem is not solvable by any computer, no matter how much time is given. Most problems that do not yield polynomial time algorithms are either optimization or decision problem. An optimization problem corresponding to people ask, what is optimal solution to problem X? Given a graph, can you find what is the optimal minimal spanning tree? And for example, the 0-1 knapsack problem, fractional knapsack problem, minimal spanning tree. Did you still remember knapsack problem? We still assume we're going to have to travel to the span, and we have a specific luggage, and they allow us to put some items there. We can only choose that item or not choose item. We want to make sure the items we bring with us in that luggage, which has most value, right? And also the luggage has an upper bound weight. And so this constraint optimization problem. And a fractional knapsack corresponding to, we have a bag, we can take as some items as possible, and some item even can cut into part. We can even take part of the items and with us, and we want to bring as much value, the most biggest value with us as possible, right? So we see this is a greedy algorithm. This is the dynamic algorithm. Did you remember? And this is the minimal spanning tree, which we use a greedy algorithm. This is the optimization problem. A decision problem is the one people expect yes or no answer. And we do not want you to say, give us the spanning tree. We want to ask, is there two spanning trees with the same minimum weight? Yes or no question, right? Does a graph G have a minimum spanning tree of weight smaller than or equal to W? An optimization problem tries to find the optimal solution. A decision problem tries to answer yes-no question. Many problems will have decision and optimization versions. For example, traveling salesman problem. And the optimization problem, people ask, find Hamiltonian cycle of minimum weight. Decision problem, is there Hamiltonian weight or Hamiltonian cycle of weight smaller than or equal to k? Some problems are decidable but intractable. As they grow large, we are unable to solve them in reasonable time. Is there a polynomial time algorithm that solves the problem? P. So this is the reason we say, give a problem, we would like to check which kind of the class this problem could be cast into. And if it casts into the P problem, if it casts into the polynomial runtime, solvable runtime problem, that's good, right? And if it's cut to another one, intractable problem, we may want to avoid this problem. We really would like to spend much time, and there's definitely no optimal results. Or you say, okay, I don't want to, I have to work on that. I cannot avoid this problem. It's an intractable problem or undecidable problem, intractable problem. And then we say, okay, you can use some specific algorithm technique to work on that. And although we cannot find the optimal results, but we expect you could find some results close to optimal. And for this reason, we have to learn the classes of problems. We have 4 classes of problems, and although they do have some relationship between these 4, they're not totally isolated. It's just to see how much detail could be. How do you define this untractability? So first, let's take a look at the basic one, and which corresponds to tractable, which corresponds to problem is solvable in reasonable time. That is the P problem. That's the class P. This corresponds to the class of decision problems that have a polynomial time deterministic algorithm. Keep in mind, this is a decision problem. We expect you have yes or no answer. And this yes or no answer, which is just need to have polynomial runtime, then they can solvable. They are solvable and to answer the yes/no question, right? So it means many problem, if it is a decision version based question, it is solvable in polynomial time, then in that case, this problem belong to the P class. And let's give a little bit details about this class P. They are solvable in all Pn time. Well, Pn is a polynomial on input size n. With n increased to infinity, the growth ratio is a polynomial. Deterministic algorithm is essentially one that always computes the correct answer. It's deterministic. It means it doesn't depend on any machine. And it's just your desktop, they can use the polynomial runtime to solve that. And sometimes some problem they cannot be deterministic algorithm, and they cannot run in a reasonable time in your laptop, in your desktop, but it could be run in the high performance computing. In many computers, the clustering together. Okay, so here we emphasize is P polynomial time deterministic algorithm. That is, we talk about the P class. Some problems in P, as what we mentioned before, polynomial runtime can solve the decision question, and fractional knapsack, minimal spanning tree, sorting. What is else? What is something else, right? What is any other problem which could be class B? And we say NP, class NP. We will talk about P and NP. What is the relationship between them? NP is a class of decision problems that are solvable in polynomial time on a long deterministic machine. Here, long deterministic machine, which is separated from the what we talked about before, polynomial deterministic machine, right? So we say here, of course, if the problem can be solved in the deterministic machine, it can also be solved in the clustering, high performance computing, right? So it means NP P problem belong to the NP problem, right? Now the question is if P is equal to NP or not, right? So why do you say P belong to NP? But do we have this sign? Is NP belong to or not, right? Okay. Good. NP can be thought of as the class of problems whose solution can be verified in the polynomial time. NP stands for long deterministic polynomial time. So NP is not because many students, even for many engineers, or as even scientists, computer scientists, they thought about NP is long polynomial, but it's wrong. It's not in this way, and it's corresponding to long deterministic polynomial term. It could be verified in polynomial term through the long deterministic machine. For example, graph coloring problem, and which has an exponential solution, but once you use the high performance computing, it could be solved in the polynomial runtime. Satisfiability SAT problem, traveling salesman problem, and all these. They also have many more. The max matching problem, graph click problem, many problems belong to this part, and which could be verified in NP in the polynomial runtime on long deterministic machine. Let's take a look at SAT problem as an example. We see that this is a basic NP complete problem. We'll go to NP complete this definition. And now let's take a look at SAT satisfiability problem. Give a Boolean expression on n variables. Can we assign values such that the expression is true? And we say give a Boolean expression on n variables. Each variable, it is a Boolean variable. Each variable has two options. To verify this expression is true or not true, we may need to check all these combinations, and such that we could have 2 to the power of n combinations. It seems easy enough, but not long deterministic polynomial term algorithm exists, but easy to verify in polynomial term, which corresponds to give an instance of this n variables, give a sequence of these n Boolean values, and you can verify. You use these n Boolean values and put this n input values into this expression. You just go through each term by each term, and we'll assume this term is a polynomial, right? That's true, and such that it's only can verify in polynomial running time. But the search space is definitely, which is the exponential in this one, but it could be run in high performance computing. The problem is NP long deterministic algorithm, guess true algorithm, check algorithm to see if it satisfies CNF formula, and this is the choose assignment. You can you guess how many, you guess different assignment you put in the, since each assignment, you can verify this assignment in polynomial term, right? So verify, given each, this we give another small example, right? It's not n, but n variables, but this is the 5 variables, right? And I give you this term, it have 4 subterms, and I give you this 6 input instance. Each row here corresponding to 1 input instance. And it is easily to verify. Give this input instance, you can easily verify this Boolean expression is true or not true, right? It's ON random to check, verify the Boolean expression. And P, let's review P and NP. And P is a class of problems that can be solved in polynomial term. NP, a set of problems for which a solution can be verified in polynomial term. Give instance, you can verify that. And P corresponding to you can decide that problem. This problem can be decided, can be tractable, can be track it in the polynomial term. Okay, P is belong to NP, right? And still, we are not sure P could be equal to NP or not, right? The question it is, most suspect not. On an August 2010 claim of the proof that P not equal to NP by Vanley Diolalica, researcher at HP Labs Palo Alto, has flaws. And some people that claim P is not equal to NP, but now people don't argue with that. No, for this video, we don't want to argue P equal to NP or not equal to NP, but we really would like you to get familiar with the one group of beautiful problems. And these beautiful problems, they can reduce to each other. If one problem can be solved in polynomial time, another problem can also be solved in polynomial time. This is what we talk about the beautiful property. A decision problem D is NP complete if and only if D belongs to NP. Every problem in NP is polynomial time reducible to D. This is we talk about the NP complete problem. And also they have one specific group of problems which comes into this class. And also many algorithm, many scholars, they try to find the approximation algorithm for that group. So this reason is also interesting to take a look. A problem R can be reduced to another problem Q if any instance of R can be rephrased to an instance of Q, the solution to which provides a solution to the instance of R. Right? So it's corresponding to, if we know Q, what is algorithm? Let's write it down here. Okay, let's see, we see the R is reducible, how to understand reduced to some another problem to Q, right? R is reduced to Q, what corresponding to that? Let's assume we know the solution or algorithm. Let's write it down here, right? We know algorithm for Q problem. This one, we have input. This is input for Q. And this is output, right? This is output, if we know about that. Now we say R is reduced to Q, corresponding to, we know a polynomial algorithm. This is a polynomial algorithm. Let's use simplifying this way. Polynomial algorithm. This polynomial algorithm can transfer the input. This is input for R to inputs of Q. They can transfer inputs of R to inputs of Q. If we can find this polynomial algorithm, then in that case, we put them together. This is what we have the solution for R. This is also, we see that since this part is polynomial algorithm, the complexity of this algorithm, complexity is tractability of R, really depending on the tractability of Q. If the Q is polynomial solvable, in that case R is polynomial solvable. If Q is untractable, it's undecidable, right? It cannot finish, it cannot be solved in polynomial time. It may take polynomial time on long deterministic machine. In that case, R will be the same way. This is corresponding to, we talk about NP complete beautiful property. This reference is also called the transformation. Intuitively, if R reduced in polynomial term to Q, R is a lot harder to solve than Q. Okay. Another term which is NP-hard and NP-complete. If R is a polynomial term reducible to Q, we denote this R is R, no, and Q, R is less than or equal to PQ, represented in this way. So the definition of NP-hard and NP-complete, if all the problems R belong to NP are polynomial term reduced to Q, then Q is NP-hard. For example, the Turing-Hunting problem, we say Q is NP-complete if Q is NP-hard. So if Q is NP-hard, then definitely it is NP-complete. And NP-hard is that specific group of problems. All the other problems can be reduced to this Q. It's a fundamental, intractable problem. Then we treat that as the NP-hard problem. Okay. And also this reducibility, if some problem can be reduced to Q, if R, it is NP-hard, in that case, of course, Q is also NP-hard. Practical implication, give a problem that is known to be NP-complete, try to solve it by designing a polynomial term algorithm, and we see, we can prove that is we can prove that, and also sometimes if people really want you to solve that, and we say we would like to find the solution close to optimal. Although there is no polynomial term runtime to find the optimal solution, but we could have polynomial term to find a solution very, very close to the optimal results. So this is go to the approximation algorithm, and this is go to our next two specific topics, linear programming and approximation algorithm. That's all for this video. Thank you for listening.